Okay, so how is everyone today? Good, I hope? All right. So today is what? The 12th. And that means that 3 Fridays from now, which means 2 plus 7 plus 7 days from now is the exam. So I'm just mentioning that so that it's kept in view. So it's like 16 days from now. It's a while, but I just want to remind you. Good. So last time we were talking about partial fractions. We're gonna do one more example of those, and then move on to the next section. So here's a nice example. So here we go. So the example is antiderivative of rational function in the numerator x to 4 minus 2x squared plus 4x plus 1 and then over x cubed minus x squared minus x plus 1 dx. All right. So you're being asked to anti-differentiate this rational function. Now, because we're in the partial fraction decomposition section, that's a pretty good hint that we're going to use partial fraction decomposition. But eventually we're going to just you're just going to be hit with this, and you don't know which one it might be. So the thing that's telling you this is, in the first place, this is a rational function, right? It's polynomial over polynomial, and moreover, it doesn't look like a substitution to me, because if we were going to do any substitution, we would have to say that u is the denominator. Okay, we'd have to say u is the denominator. It would make no sense to say u is the numerator, because then we wouldn't be able to cover at all the denominator with the substitution. It wouldn't work. Furthermore, concerning this rational function, so we're anti-differentiating a rational function so just having a look at it, it doesn't appear to me to be like immediately obvious what the answer is. So the first question that you should ask yourself, besides do I see the answer immediately, is you should ask, is it proper? Okay, so I heard no. Why is the answer no? I agree. So for a fraction, like integer over integer, like 8 over 5, is 8 over 5 proper? No. It is not, because 8's more than 5. The proper way to write it, 8 over, what did I say, 5? 5 over 8. 5 over 8 is proper. But if you have the fraction 8 over 5, that's a perfectly legitimate fraction, 8 over 5. Yeah, but you want to write it as 1 and 3/5, because there's 1, the integer part is 1, and the proper fractional part is 3/5. Now 3/5 is proper because 3 is less than 5. How about 8 over 8? Is that proper? It is not. Because to be proper, the denominator has to be bigger, strictly, than the numerator. So now biggerness means what in the case of rational functions? How are we measuring the bigness? By the degree, yeah. By the degree. So even if I put some coefficient, presently the coefficient is 1, even if I put some big coefficient here like 2,414, it would still not be proper, because degree. All right, so the answer is no, because it's a degree 4 over degree 3. But, and you know, then you could just look at that, go back to integers, and then ask yourself, well, is 4 over 3 proper? In the integer sense, it is not. So this rational function is not proper in the polynomial sense. So since it's not proper, then what do we do? Long division, right? So, you know, to be clear, the integer problem. So what I'm going to write down is not part of the solution to this exercise. This is the kind of thing that you might have done, like, you know, like in like 5th grade or something. I can't remember. So, you know, I could say, well, in the first case, how about 1, 2, 3 divide by 18? So is that proper? No. It is not. So then we could represent this as as the sum of an integer and a proper fraction by doing the following. We could say, okay, divide 1, 2, 3 by 18. And then you get from that the quotient and the remainder. So then 1, 2, 3, like this. Oh, look, I made it 8. I'm going to make, sorry, I hate it when the instructor does this, but I'm going to do it. Very sorry. I'm going to change the 2 to a 9. That makes the problem slightly better. Okay. So you end up writing something that looks like that. And then if, you know, I don't know what your grade school was like, but at my grade school, this is when the teacher did 193 is in the house and 18 is outside the house, but 18 wants to come in. You know, how many times can 18 go in? 10 times, because what you do is, because there's 2 digits there, you take the first 2 digits there, and you're asking how many times can 18 go into 19? Once, right? So you write a 1. And you make it line up. Because we were considering 19, that 1 lines up with the least digit of the 19. So then now this 1 realizes that it's doing a long division problem, and in despair, it jumps off the house. It jumps off the house, hits the 18 on the way down, multiplies to become 18. You know, if it was a 2, it'd be 36. You write the 18 right here, okay? And then you're going to subtract. But you must understand that that 1 is not actually a 1. What is it actually? It's actually a 10. And this 18 is not actually an 18. It's actually 180. But we're ignoring the least significant digits currently. Okay, so we're ignoring that 3 there. And then now you perform the subtraction. Well, what is 19 minus 18? It's 1. And then this carry down thing that your teacher told you, you know, the carry down thing, what that really means is that's where you're finally re-acknowledging that that's not really a 1, it's a 10, and that's not really an 18, that's 180. So now you carry down the 3. Blah. And so now 18 wants to come in. How many times can 18 go into 13? 0 times. So then you write a 0 right here, and then in despair, the 0 because it realizes it's in a long division problem, it jumps off the house, it hits the 18 on the way down, it multiplies with the 18 to make a 0, and then you subtract that much and get 13. Okay, and there's nothing more to carry down, which means that the process has now terminated. So as a result, what that's telling you 2 numbers. This procedure has 2 outputs. One of them is this number, and the other one is this number. What is this number called? This is the quotient. A 10, yeah, I agree. Quotient. And what's this one called? The remainder. And what that's telling you is that 193 is equal to 1/8 multiply 10 add 13. That's what that procedure is telling you, is that these two, 193 and 18, were the inputs. 10 and 13 were the outputs. Okay, and if you like, if I put a pile of 193 M&Ms in front of you, and I said, please make groups of size 18, you could make 10 such groups, and then there would be 13 left over. That's what that means. So if we take this equation and divide both sides by 10, by 18, then what? Then we'd get 193 over 18. That would be the new left-hand side. And then for this term, if you divide by 18, what do you get? 10. And then for this term, you get 13 over 18. Now, what I want you to observe from this is that here's a fraction that we began with. Is it proper? No. It is not. But we've performed this procedure, and now we've represented it as an integer plus another fraction, and that fraction is proper. Okay, everybody got the idea? So what I'm telling you is that, in math, especially, I'm now especially talking to math majors, there are extreme and deep similarities between the integers and the polynomials. So what I'm telling you is that what we're going to do now is that we have a ratio, a fraction of polynomials, and what we're going to do is and it's not proper. What we're going to do is we're going to perform a procedure just like this, and the output is going to be two polynomials, one of which is the quotient, the other the remainder, and it will be the case that the result tells us how to represent this improper rational function as the sum of a polynomial plus another rational function, and this new rational function will be proper. Okay? So now the polynomial problem, you can write it like this. So this is the thing that needs to be divided. So it's what goes in the house. And here's part of the trick to make sure that this is right. So notice that this polynomial in the numerator and that polynomial in the denominator, they both have 4 terms. By the way, what are terms? Those are things that are added and subtracted, right? So you can see that among the items in the numerator, there's 4 of them that are being added or subtracted. So there's 4 terms. This one also has 4 terms, right? Concerning just that right there, that's in between my fingers there, that's a single term, because there's no adds and subtracts, but that single term has 2 factors. Because what are factors? Things that are multiplied and divided. That's what factor means. Things that are added and subtracted are terms. Things that are multiplied and divided are called factors. All right, 4 factors, 4 factors. 4 terms, 4 terms. But because this one has 4 terms and that one has 4 terms, and because that one has a higher degree than that one, that means that this one has in a sense, a quote missing term. What's missing? The degree 3 term, right? So when you're performing long division, you must write in all of the terms, even if there are 0 of them. Otherwise, you are in grave danger of making more or less just a bookkeeping error. So to get this right, I'll write x to 4, and then now I'm going to write plus 0x cubed. That's what I mean, is that's the missing term. You need to write it minus 2x squared plus 4x plus 1. That's what's inside the house. What's outside the house is x cubed. Notice that one has all of its terms. X cubed minus x squared minus x plus 1. And if it was good for 4th grade, then it's good now. Want to come in? So remember, when you were doing this in 4th grade or whatever, you did this thing where you were just considering the leftmost digits and things like that. We have exactly similar thing, except now we're considering leftmost terms. So the leftmost term outside is this one. The leftmost term inside is this one. So we're only considering leftmost terms. So the way that you do it is that you take these leftmost terms, and then over on the side you make a calculation, and you could say, okay, what if I just consider the leftmost terms and do this? Okay, if we perform that cancellation, what do we get? X. We get an x. So x, that's the thing that gets put on top of the house. Right there. And then that x, realizing it's in a long division problem, in despair, jumps off the house. Okay, hits the divisor on the way down. So now you take that, that x and you multiply it by the divisor. That's x plus 1. So that's just like 1 times 18 and 0 times 18. You multiply that out and collect like terms. You write it under the current dividend. So if you multiply that out and write it right here, you need to make the terms line up. So that'd be x to 4, and then subtract x to 3, and then subtract x to 2, and then add an x. Whoops, add an x. Okay, so that times that. So what I'm saying is that this went right there. Now, when I wrote that 18 under there, I said, now you write the 18 there, and then what do we do with that 18? Subtract. You subtract. So I wrote it. I haven't done the subtracty bit yet. So now I'm going to write it, but you tell me what's not correct. So I'll write, I need to subtract. Right. All the terms, right? If you so desired, you could flip all the signs, but I don't like doing it that way. That messes me up. So I just put these in parentheses like that. Okay. Now, you perform the subtraction. And now notice that we have x to 4, and then we're going to subtract away x to 4. So how many x to 4s will we have? 0. Of course we will have 0 of them. That is the whole point. If it were not the case that you got rid of the highest degree term, that would mean that you made an error. That's what that would mean. It would be just like if I said here, you know, if I asked how many groups of size 18 can you take away from 19, and you said none. Well, that's not right. Or if I said if the numbers were different, and I said if we had 17 M&Ms, how many groups of size 2 can you take? And you said 3. Well, you can do more than that, right? Okay, so doing that. Subtracting that, 0x cubed minus a negative x cubed gives a single x cubed. Negative 2 of those minus a negative 1 gives minus x squared. 4 of those minus 1 of those gives 3 of those. And then carry down the 1. Any questions so far? So now, you know, how do you detect when the process terminates?
Can't go in anymore.
Okay, how do you detect when you cannot go in anymore?
The degree is lower, the power than the number on the outside is larger than the remainder.
Very good. So the current leading term inside is this one. 3 over 3. Not proper yet. We have to get this leading term to be less. Okay, so then what we'll do is we take the leading term inside and the leading term outside and do a little calculation over here. X cubed over x cubed. If you make that cancellation, what do you get?
1.
You get 1. So now you take that 1, and it gets put on the top, but you know, it gets put right here. You know, so that things are lining up, and then in desperation, that 1 jumps off, hits the dividend on the way down. So you write 1 multiplied by all that, x cubed minus x squared minus x plus 1. You multiply that out. You write all that under here, so that'd be x cubed minus x squared minus x plus 1. And then we need, so what I'm saying is that this, oh my blue pen. I use these pens because they show up best on the projector, but to some extent they are kind of a pain to deal with. This went right there, and then now I need to subtract that. How many x cubes will we have when that's done? 0, because of course we'll have 0. That was the whole point. So we'll have no cubes, and just as a coincidence, we will also have no squares. And then 3x minus negative x would be 4x. And then 1 minus 1 would be 0. So just 4x there. All right. Now, the leading term inside the house is now this. So what? We're done. Why are we done? It's proper now because it'll be degree 1 over degree 3. 1 is less than 3. That's the stopping condition. So as a result, what that's telling us is that this x plus 1 is the quotient, and 4x is the remainder. So it's telling us, we can say, therefore, what we're doing here is that this thing, x to 4, and then I'll omit the 0, minus 2x squared plus 4x plus 1, this thing that we were dividing up, is equal to, the divisor was that, x cubed minus x squared minus x plus 1, and then we multiply that by the quotient that we found, which was x plus 1, and then we add to that the remainder. That's what that procedure is telling us. These two things were the inputs to the procedure. These two things were the outputs. Now, notice that the question is about this. Okay? The question is about this fraction. And at the present time, we don't have a fraction. So how do we get to the fraction we were talking about originally? Yeah, we divide both sides by that cubic. So if we divide both sides by that cubic, then we get x to 4 minus 2x squared plus 4x plus 1. Divide by that cubic there, x cubed minus x squared minus x plus 1. Okay, so concerning this term, dividing that term by the cubic, what do you get? X plus 1. No, it is not necessary to write those parentheses, but I'm doing that on purpose. And then plus, dividing that term by the cubic, you get this. So what I want you to observe, just like in grade school, an improper fraction can be represented as an integer plus a proper fraction. And now, an improper rational function can be expressed as a polynomial plus a proper rational function. Polynomials and integers are analogous. Proper fractions and proper rational functions are analogous. Any questions about this? So notice that the question started with this calculus question, and we've like gone way down the rabbit hole, and we haven't done any calculus. Right? What I'm saying is that instead of anti-differentiating this, because this is algebraically equivalent to that, we can anti-differentiate that. Okay? So, again, no calculus has occurred yet. So, continuing, the antiderivative of what we were doing, whatever it is, it's got to be equal to the antiderivative of x plus 1 plus 4x over x cubed minus x squared minus x plus 1. So now as for this, that's a polynomial, right? You can do its antiderivative in your sleep. It's x squared over 2 plus x. Okay, so I'll ignore that bit because that's easy now. The question is how do you do that? Oh. Sorry? Yes, so yeah, you can distribute the antiderivative across that one. So that's what I meant, is that one's easy. But in the end, the question is how do you do that one? You got to factor it. Sorry? I didn't hear what you said, sorry? Well, concerning those right there, they don't all have an x, so you can't factor x out of all of them, just out of the. But that won't help in the end. Okay, so now I leave it to you. You're going to have to figure out how to do this because I did this bit because I find that I basically need to do that. Otherwise, y'all will be asleep at the wheel. But there's more stuff that you know, how to factor a cubic. Okay, so then one way to factor a cubic is using the rational zeros theorem, where that tells you a bunch of guesses, like you should guess one of these, and then you guess them, and then you perform synthetic division, to suss out which one is the right one, and then you can get it. Okay, so I'm telling you that that's something you need to look up. Okay, so we need to factor the cubic, x cubed minus x squared. This is something that you need to look up. So, magic. Not really. You need to look this up. When you factor it, it becomes the following. It becomes x minus 1 multiplied by x minus 1 multiplied by x plus 1. Okay, so of course that could be written as x minus 1 squared times x plus 1. So what we're dealing with, concerning, ignoring the easy bit and just looking at that, we're looking at something that looks like this: 4x over x minus 1 squared multiplied by x plus 1. So now that can be decomposed using a partial fraction decomposition. So notice that this x plus 1, what's its multiplicity? It's 1. Therefore, we know that in the decomposition, there should be something that looks like a over x plus 1, corresponding to that. Okay. Similarly, concerning that factor, what is its multiplicity? It's 2. Therefore, corresponding to that, there will be 2 terms on the right-hand side, not just 1, but 2. If the multiplicity was 22, there'd be 22 terms over here. So what you get is you get b over x minus 1. Okay. But you also get what? C over x minus 1. What? Just like that? Squared. Okay, so that's something that you have to know. So now we want to figure this out as quick as may be. So now I'm going to multiply both sides of the equation by the denominator of the left-hand side. So I'm going to multiply both sides by that. Doing that, the new left-hand side is 4x. The new right-hand side, when you do that cancellation, we'll have a multiplied by x minus 1 squared. Because the x plus 1 will cancel, we'll have b multiplied by x minus 1 times x plus 1, because only one of them will cancel. And then we'll have c multiplied by what?
X plus 1.
Just x plus 1, because we get 2 cancellations, like that. So now, considering this then, I'll do some neat trickery here and say that there's 2 magic values. What are the magic values? 1 and negative 1. Because concerning the right-hand side, notice that if you plug in 1, that term goes away, and that term goes away. So at x equal 1, we obtain the equation 4 is equal to 0 plus 0 plus 2c. Therefore, c is what? 2. What's another magic value? -1. So at -1, we obtain the equation -4 is equal to, well, at -1, that would be -2 square that, so that'd be 4a. At -1, that term is 0. At -1, that term is 0. So we have -4 is 4a, and as a result, what? Very good. A is -1. So now we've figured out two things. Now what? Okay, I like it. So what I would like for you to observe is that notice that there's 3 unknowns, but we only have 2 magic values, right? So there's not like another magic value to do it. So the way that I'm going to do it is I'm going to do as he said, is I'll plug in C and A, okay, and then multiply out and collect like terms. There will still be a B hanging around when you do that. And the thing is that how many x's are on the left? Well, 4, right? And then you'll be able to use that information by comparing it with the b's on the right, and you'll be able to say, b is whatever. Okay? So I'll omit that part for time. So now but I'll write down what it was that you would do. So now you multiply out and collect and compare coefficients. To obtain b is what? B is 2. Okay. Therefore, this thing right there, we can decompose it like this. So continuing the original one, it would be antiderivative x plus 1. So keeping that polynomial there, and then plus, what do we say? A over x plus 1, where a is that. So plus -1 over x plus 1, plus b over x minus 1, where b is that. So plus 2 over x minus 1, and then plus c, which is 2, over x minus 1 squared. Again, I want to point out that no calculus whatsoever has occurred. No calculus. No calculus because we couldn't do any calculus yet. So that being the case, notice that we now have 4 terms that are being anti-differentiated. That one, that one, that one, and that one. Now, because the antiderivative distributes over terms, that means that we can consider each one of them separately, and that's good. So they're all pretty straightforward, but so I'll just do them quickly. Antiderivative of this one, that'd be what? X squared over 2 plus x. Antiderivative of that one would be plus negative logarithm of absolute value of x plus 1. Antiderivative of that one would be plus 2 logarithm absolute x minus 1. And then the most common error that I find that students make here is that they try to do logarithm with this one. Can you do logarithm with this one? You cannot, because its exponent is 2, right? But a fairly straightforward substitution will give you that this should be, in fact, that 2 is that 2, and then reckoning this to be like u to -2, it would be x minus 1 with exponent -1 divided by the new exponent like that. And then now plus a constant. So I'll write what? No, not plus c. You can't write plus c. Plus k. Why can't you write plus c? You already said c was 2. Okay. Good. Any question about this? Fine. So now, here's the deal, is that y'all now have learned like a variety of anti-differentiation techniques. So you know, like, well, you know some specific antiderivatives by heart, say. Like, you know that the antiderivative of sine is? Negative cosine, and you know that the antiderivative... So you know some things, right? Hopefully. Okay. Then you know that if you're anti-differentiating a sum, and you know the terms, then you can just anti-differentiate the terms and then add those terms up, add the results up, which is to say antiderivative distributes across addition. And you know how to do anti-differentiation by parts. You know how to do a variety of other algebraic techniques like this thing that we just did, partial fraction decomposition. And you by now know that if you find yourself anti-differentiating a rational function, if it's not proper, the first order of business is what? Is to perform a division so that it's the sum of a polynomial, which is easy, and another rational function, which is proper. And then, if needs be, at that time, you decompose. So you know, like, all these things now. And the purpose of the next section is basically, now we're going to start giving you antiderivatives, and it's not going to be, today we're in the section blah, and here's an example of doing blah. Rather, it's just going to be, hey, here's an antiderivative. And you have to figure out what is it that you must do. Okay? Does everybody understand the context? Now, that being said, I want to make sure something is clear. This is section 7.5. What is its title? I remember the title being not very impressive. It's called in the textbook. It's called strategy for integration, but even the title is wrong. It's actually strategy for anti-differentiation. And it doesn't bother to give the name for this, but the author's kind of describing something and then doesn't name it. I don't really care for that. The name for the strategy, it has a name, and if you care to look it up, it is called the Risch procedure. So you could look that up on Google. Now, here's the deal. We have this set of functions called elementary functions. So elementary functions, okay, are functions essentially like every function that you know. Okay, so things like sine, cosine, principal sine, principal cosine, okay, exponential, which is to say things like e to x, hyperbolic sine, hyperbolic cosine, and all of the hyperbolic things, log. So any function that you know by name, that is included in the list of so-called elementary functions. So now, that all of these, and the other ones that you know, unless you happen to know something really strange, these are the elementary functions. All right. Now, concerning these, so if f and g are elementary functions, so if you have any two of them, sine and cosine, exponential and square root, any two that you care to name, then f plus g, f minus g, f multiply g, f divide g, f caret g, which is to say f of x with exponent g of x, and f composed with g, those are all elementary. All elementary. EFs. So that just means if you take any two elementary functions, which I'm just loosely saying is every function that you know of, and then you add, subtract, multiply, divide, use one as an exponent, or compose them, the result is still elementary. And that kind of makes sense because that's the way numbers work, except you can't compose numbers. All right. So here's the deal, and this is the whole problem, is that viewing the derivative as a machine, viewing the derivative as a machine, like you could put an input into it and just see what it does. If you put an elementary function in, then some other elementary function is going to come out. Usually it's different. Like if you put x squared in, what comes out? 2x. But it doesn't always have to be different. What kind of function? What's an example of a function when you put it in, the same thing comes back out? Exponential, right? All right. So derivative works that way. You take any elementary function that you care to write down. You differentiate it, and you get another elementary function. So that's neat. Then you might ask, well, what is the name of the thing when you run the derivative machine in reverse? Anti-differentiate. Anti-differentiate does not have this property. Antiderivative does not work this way. So, in fact, if you take an elementary function and you put it into the antiderivative machine, a new function will come out. But it is almost certainly not an elementary function. Oh, really? So what I want you to understand is like, you know what a rope is? Just a piece of rope, you know? Which one is, no, I've never heard of this thing, this rope. Which one is easier? Is it easier to pull a rope or to push a rope? Derivative is pulling a rope. It's really easy. Antiderivative is pushing the rope. That's a trick. Okay? And it's only going to work under very special circumstances. That's why when you might have the sense that calculating antiderivatives is so much more adventurous than calculating derivatives. You could write down any kind of crazy function that you want and then calculate its derivative, and you know all the rules. You know them all. There aren't any others. But if you write down some crazy function and you say compute its antiderivative, what I'm telling you is that it is virtually certain. If you randomly select an elementary function, it is virtually certain that you cannot calculate that antiderivative and get another elementary function. Okay, so the meaning of this is neatly expressed in the following. So how about what if I ask you to calculate the derivative of the exponential of x squared? Is that a thing that you can do? Yeah, because the input symbol is x, and before the x gets to the exponential, we're saying we're going to square the x, and then we're going to give it to the exponential. So that's really a composition of two things, squaring and exponential. So what rule will we need to use? The chain rule. So according to the chain rule, this should be the derivative of the, this should be the exponential part, the outermost thing. So exponential of x squared. Now, if that x squared, if that x squared were exactly x, we'd be finished. But it's not. So then to include what the x squared does is now we have to multiply by the derivative of x squared. And then what's the derivative of x squared? 2x. So exponential of x squared, and then multiply 2x. What I want you to see from this is that exponential is elementary. Polynomials are elementary. the composition of those is elementary. So exponential of x squared is elementary. We calculated its derivative, and we got that function, which is elementary, that function, which is elementary, and the product of those two functions is elementary. Okay, no big deal. Whereas if I ask you to do this, if I ask you to do that, you know, instead of differentiating it, maybe you anti-differentiate it. So now, there is an answer in some sort of like cosmic sense, but there is not an elementary function whose derivative is that. There isn't one. And understand what I mean. I don't mean like I know it, but I'm refusing to tell you. I don't mean like if you go on and learn some more stuff, you could figure it out at that time. I mean that there is not one. It doesn't exist in the rules of the universe. There isn't one. Cannot be done. All right. So that's why anti-differentiating is such a trickier thing. Now, for those of you that are math majors and just want to know why should it be this way, the reason is because the derivative has a property called closedness. The derivative is closed, and because antiderivative is doing that, but inversely, going backwards, it's not possible for an operation to be closed in the one direction and also closed in the other direction. So the closedness of derivative in the forward direction causes the non-closedness, and by the way, that doesn't mean open, in the other direction. Good. So now let's do it. So there's a table in the book. That table right there. So in this class, it is expected that you should memorize all 20 of these. So every single one of them. So what I mean is that every time you're doing an antiderivative, every time, you will exit through one of these 20 doors. Now, I would never just write down antiderivative of sine of x. Right? I'd make it more entertaining, you know. Maybe like antiderivative of sine of 5x, you know. And but you know, with a mild substitution, you change it into exactly that form, and then you exit through door number 5. So all of the antiderivative problems that exist in this class, you will exit through one of these doors. So you must memorize these. Okay, so you know, do that. Good. So let's have an example. So what if I give you, say, this one, antiderivative of x over x squared minus 1 dx. All right. What do you do? Well, according to the Risch procedure, which is what the name of this is, the first thing that you do is you perform perform any and all algebraic steps that you can imagine. Algebra-ness. So concerning this, you know, this would be things like simplifying something like x squared times x cubed to x to 5. That's what you do. You know, something like that. Okay, any and all algebraic steps that you can imagine. Okay, and then you ask, after doing all of those algebraic simplifications, is it one of the 20? Okay, so there's no algebraic things to do here. Okay, so then no. So 1.1 is like an empty step. 1.2, then you ask a question like, well, is it possible to do some other algebraic thing? For example, is it possible or necessary to do a long division? So do we need to do a long division? No, because it's a rational function, but it's proper. So we need not perform a long division. All right. Still with just algebraic things, no calculus consideration yet. Can we do a partial fraction decomposition? Could we do that? Here the answer is yes. We could perform a partial fraction decomposition. But, so I hope someone will say but. But what? Okay. So there's a few more of these ones, okay, and I'm up against the clock, so I got to speed through this next bit. So supposing that we're not set. So by the way, you can do a partial fraction decomposition, right? Because you could factor that as x plus 1 multiplied by x minus 1, and then do exactly the same thing that we did earlier. Okay, you could do that, and there'd be nothing wrong with that. Now, the next step is to ask, could we somehow do a variable differential substitution? Which is to say, y'all probably called it a U substitution. So can you do a U substitution? In fact you can, right? Can you see it? Okay, if you couldn't do a variable differential substitution, then you should ask, can you do it by parts? Okay, and the answer might be yes or no. If you can't do it by parts, you could ask, well, can I do some kind of trig substitution? By the way, another item up here in the algebra, 1.4, is all the different trig identities that you have to memorize. You know, like the power reduction formula, where you take a cosine squared and double the angle to make something that's not squared. Okay, so then this procedure, this is what we're doing. This is a flowchart. Now I'll write out the full flowchart next time, but what I want you to see is concerning this exercise, there's two outs. You can either do a partial fraction decomposition, two outs so far, or you could do a variable differential substitution. Either one. So just so we have something to complete, I'll do it very quickly. So I'll do the substitution because that seems easiest to me. U is that. du over 2 is that. After this substitution, we obtain what? Antiderivative 1 over u du over 2. Now, aside from this division by 2, do you observe that that's door number 2? It's door number 2. So what I'm telling you is that every single antiderivative problem, no matter how it's stated, after these steps, you will exit through one of these doors. Do you have a question? All of the various trig identities that we talked about. So plus a constant. Okay, good. So I hope you have a wonderful Wednesday.